We saw in the last video that calculating a trigonometric value looks complicated, and our calculators have to go through quite a few computations in order to get some kind of decimal number for these. However, there are some special angles for which we do know the exact computation, and that's what I want to do in this video, the exact trigonometric values. Okay. And these may have been known in ancient times. I'm not totally sure, but seems like they probably did think about this, I would think. Anyway, first of all, let's look at the equilateral triangle. So you probably remember that an equilateral triangle has the same length on each side, which also makes the total of 180 degrees inside divided equally. So all these are 60-degree angles. All right, now, so I'm going to label the sides. Let's call them length 1. And I'm going to bisect this angle, forming a perpendicular bisector. And this angle is 60 degrees. This angle is 30 degrees. That's 90. So it's the 30-60-90 triangle, as we like to call it. The 30-60-90 triangle. And I think I'm going to draw a larger version of this, so I can work on that. Alright, so here's a larger version of our 30-degree, 60-degree, 90-degree triangle. And the hypotenuse is length 1. The height of the triangle, since we bisected this angle, perpendicular bisector, this is going to be 1/2, that'll be 1/2. So the height of this triangle is 1/2. And so already we know that the sine of 30 degrees is 1/2 divided by 1, which equals 1/2. So sine of 30 degrees is 1/2. I'll write that down for your notes. But let's get the other side. And so if I call this temporarily x, then Pythagorean theorem says that x squared plus 1/2 squared equals to 1 squared. So x squared plus 1/4 is 1. Let's subtract 1/4 from both sides. X squared would be 3/4. And then we'll take the square root. And it will stick to the positive square root because I can't have a negative length side. So x would be the square root of 3/4. Now the denominator is the square root of 4, which is exactly 2. So this ends up being the square root of 3 over 2. There we go. So the base of our triangle is the square root of 3 over 2. All right. So now we can do some exact computations. The cosine of 30 degrees is the adjacent over hypotenuse, so it would be this number divided by 1. It would be that number, wouldn't it? So cosine of 30 degrees is the square root of 3 over 2. The sine of 30 degrees, as it says, 1/2 because it's opposite over hypotenuse. That's 1/2. And then the tangent 30 degrees is opposite over adjacent. So that's 1/2 divided by the square root of 3 over 2. Now, I'm dividing by this number. I'm going to invert and multiply. So we have 1/2 times 2 over the square root of 3. And the 2's cancel, leaving 1 over the square root of 3. And that's often how I remember it, but a little more traditionally we would rationalize denominators, and so by multiplying top and bottom by square root of 3, this becomes just 3. And on top I've got the square root of 3 over 3. So tangent of 30 degrees is square root of 3 over 3. There you go. So we have exact computations for the trig functions for 30 degrees. And we should be able to get 60 degrees, shouldn't we? Well, it's kind of interesting. For 60 degrees, and they're complementary angles, 30 degrees and 60 degrees add up to 90. That makes them complementary. And so the But anyway, it works out this way. The cosine of 60 degrees is, now I'm working from this angle. Okay, cosine would be adjacent divided by hypotenuse, so it would be 1/2 divided by 1. That would be 1/2. And the sine of 60 degrees relative to 60 degrees is opposite over adjacent. So square root of 3 over 2 divided by 1, that's square root of 3 over 2. And what about the tangent of 60 degrees? Well, it turns out it's a reciprocal. It's going to be the square root of 3, but we can go through the act here. Tangent would be opposite over adjacent, so square root of 3 over 2 divided by 1/2 is the square root of 3 over 2 times 2 over 1. The 2's cancel. I get the square root of 3. So there you go. There's the square root of 3. So now I've got the basic trig functions for 30 degrees and 60 degrees. And you should memorize these. Okay, now hopefully you'll just get it memorized through practice. Memorize through practice, because it would be hard to just sit there and think, okay, cosine of 30 degrees is square root of 3 over 2, sine of 30 degrees is 1/2. That's not an easy way to memorize things. So if you practice this, a lot of book problems, you'll eventually get all these down pretty well. Now then, obviously 1/2 is 0.5, but the square root of 3 over 2, it's nice to know these. Square root of 3 over 2 is about 0.866. Okay, you could punch it on a calculator, it rounds off to 0.866. No, I'm like 99.9% sure of that, but let me make sure I'm not making an error. Square root of 3 divided by 2. 0.866, yeah, rounded to 3 places. And it's useful to have an idea what their sizes are. It really is. And this will make apparent sense later on when we do a lot of problems on a circle. Trig problems on a circle, it's nice to know the relative values of these numbers. Now the square root of 3 over 3 is about 0.577. I better look that one up just to make sure. Square root of 3 divided by 3. I know I'm very close. 0.577. Okay, I'm correct on that. And so tangent of 30 degrees is less than 1. It's a little bigger than 1/2. 0.577. Square root of 3 over 2 is close to 1. 0.866. And finally, the square root of 3 is about 1.732, which is larger than 1. So it turns out, and we'll dwell on this in a later video, the sines and cosines are always between 0 and 1 on a right triangle. Secants and cosecants are always greater than 1 on a right triangle because they're reciprocals. The tangent can be any number from 0 to infinity. Well, it doesn't equal infinity, but any number greater or equal to 0 could be a tangent or a cotangent. And so here the tangent is larger than 1. If you punched in on your calculator tangent of 89.9999 degrees, you'll get a very large number. But if you punch in tangent of 90, you'll get an error because it's trying to divide by 0. So we'll go over that later on. But anyway, I want you to have kind of an idea of these relative values. It's kind of nice to know this. Okay, so now from here you could also do the other 3 trig functions. The secant of 60 degrees is going to be 2. Okay. The cosecant of 60 degrees is 2 divided by the square root of 3. 2 divided by the square root of 3 is like 2 times the square root of 3 over 3, something like that. Of course, the cotangent of 60 is this number. 1 divided by the square root of 3 ends up being s. So cotangent of 60 is equal to the tangent of 30. Cotangent of 30 turns out being equal to the tangent of 60. And actually, when you go back and forth here, the cosine of 60 is 1/2, but the sine of 30 is 1/2. So cosine and sine of these complementary angles are actually equal. Same here. 30 degrees, 60 degrees, those are complementary, they add up to 90, and they have the same value. So that's a nice observation to know about. You know, how are you going to keep all this stuff in your head? Through practice. Through practice. Memorizing some of this is not so critical. I do think, though, you absolutely need to know these 6 values. Okay, you got to get that memorized. It's going to help you and save you time like you wouldn't believe. So, at some point, try to drill those into your head through practice. Through practice. Okay, so that's the 30, 60, 90 triangle. I'm going to erase the board, and we'll look at the 45 degree angle. We just figured out the exact trigonometric values for 30 degrees and 60 degrees. Came from the 30, 60, 90 triangle, which is half of a equilateral triangle. I forgot to mention or point out that, okay, well, 30 degrees is pi over 6 and radians, and 60 degrees is pi over 3 radians. So you also need to learn this in radians. And trust me on this, it's going to help you throughout this course to get these basic values in your head. It'll help you to do problems. Okay, now then, another one we can calculate exactly is using the isosceles right triangle. What in the world is that? All right, so I have a right triangle, and isosceles means that 2 of the sides have equal length. But it's a right triangle, and so you can't duplicate the hypotenuse in a right triangle, but these 2 sides are equal. And so let's suppose let's call them length 1. Call them length 1. And that means the diagonal is going to be the square root of 2. Because you have 1 squared plus 1 squared, that's 1 plus 1 is 2. So this side squared is 2. That side is equal to the square root of 2. There you go. So, now, isosceles triangles, the opposite sides to the equal length sides are equal in measurement. So if that's 90 degrees, that means the other 90 degrees get split up equally into 45 degree angles. Alright, so basically we're looking at 45 degree angles, or what's that in radians? 45 is pi over 4. 1/4 of a half circle is 45 degrees. Pi over 4. Alright, so this goes pretty straightforward here. The cosine of 45 degrees would be 1 divided by the square root of 2. And it's traditional to rationalize the denominator, so you want to look at that as multiplied by square root of 2 over 2, and we get square root of 2 divided by 2. Square root of 2 over 2. So cosine of 45 degrees is square root of 2 over 2. Now look at that. The sine of 45 degrees is the same number, isn't it? Because it's also 1 divided by square root of 2. So sine 45 degrees is square root of 2 over 2. Alright, the only time sine and cosine are equal at the same angle are at 45 degrees and also 225 degrees. And we can't do 225 degrees on a right triangle. They'll have to wait until we look at circles and trigonometry. But the only place where they're equal to each other is either 45 or 225. Okay, what about tangent? Tangent is very nice here. Tangent is opposite over adjacent, 1 over 1, which is 1. So tangent of 45 degrees is 1. So there you go. And by the way, these are approximately 0.707. Okay, 0.707 is the approximate decimal for square root of 2 over 2. Okay, it's also good to know that one. And so there you go. Something about tangent, by the way. If you think about, let me generalize it with another triangle. I'll work down here with this other triangle. All right, so I think it's kind of nice because you can kind of see it here in these numbers. But let me draw a triangle. All right, so I'm going to draw a triangle. So here's a triangle that I'm placing on the XY plane. And I want one corner of it to touch the origin. And so we have, here's a point on the plane, x comma y. And which means to go from 0, 0 up to xy, you go right x units and up y units. Okay. See, in class I would ask you, oh, well, okay, if that's xy, what's this side, what's that side? I wish I could ask that and wait for you to answer for me. So, because I think that's the one. Yeah, you have some advantage. You can watch these videos and replay them if you need to. The bad news is that we can't have a discussion, a live discussion. That's why I think you know, there are some weaknesses to online instruction. But what do you do? But in class, I would say, well, if that's xy, then how long is the base? How long is the height? And after a minute or two, someone will say, well, I think that's x and this is y. Yeah, of course, because you go from here to here, you have to go right x units and up y units, don't you? Okay, now then, here's angle theta. And the tangent of theta is rise over run, isn't it? Rise over run, y over x. So you see, tangent also represents the slope of a line passing through the origin with that angle. Think of the angle as from the positive x-axis rotated counterclockwise. That's our angle. The tangent of the angle is the slope of the line going through the origin. So that's why this tangent is 1. Okay, the slope is 1 is up 1 over 1. Okay, up 1 over 1 equals 1. All right. So there you have it. And that's why the tangent of 30 degrees is about 0.577 because the slope is not as big. The tangent of 60 degrees, that's a steeper line. That's why it's the square root of 3, 1.732. And so anyway, tangent enjoys that distinction. Okay, that it's related to slope in the plane of certain lines that pass through the origin. Okay, so, and again, 45 degrees is pi over 4. So, we have these mapped out now. There are other exact values we can calculate. For example, if I wanted to know the cosine of 15 degrees, there's a way to do it. And because we're going to develop later on an identity which allows us to express the sine or cosine or tangent of half of an angle, theta over 2. I mean, there's an identity for that. And by identity, I mean there's a formula. There's an expression that represents the cosine of half of an angle or sine of half an angle. So we could calculate the exact values for cosine or sine or tangent for, we'll say, 15 degrees. And we can take half of that, 7.5 degrees. Half of that is, what, 3 3/4 degrees. And you can keep on going by halves. And unfortunately, you can't get to 1 degree. You can, however, it is possible to calculate the exact value for sine or cosine or tangent of 3 degrees. That's a little tricky because you have to go through, there's a way to figure out 36 degrees in exact form. 36 degrees is related to pentagons, so I don't know if I get to that in these videos. It's kind of interesting though. And so I've actually done it. I have calculated in exact form the sine of 3 degrees, and it's about this long. It's complicated. By exact form, I mean it's not in decimal form. It's in fractions and square roots, and maybe fourth roots forms. It's all kinds of roots and radicals. That's the exact form, not the decimal form. All right. So at some point, that's not very practical, is it? It's more of a math curiosity that you can do that, because in real life we just pick up a calculator. But it would be, and I'll go back to this later. It would be darn near impossible to get the sine of 1 degree. I think it's possible to calculate the exact value for sine of 1 degree, but it's a humongous mess. I've never tried it. So, okay, there we go. So let's I'll do a few problems practicing these.